Okay, this can be a fun thing to talk about. Newton's law of cooling actually is an application of exponential functions. Okay, so let me show you what we have here. We have a kind of a complicated looking formula here, but notice in this formula you have a number times e to the kt. So it sort of falls in line with the population and radioactive decay that we were talking about. So the formula for Newton's law of cooling is little t represents the elapsed time. Capital T naught is the initial temperature of an object. Capital T with the subscript E is the temperature of the environment, and then capital T is actually the temperature at any time t, and of course K is a constant. So let me show you how this works. Let's say a can of soft drink takes 5 minutes to cool from 75 degrees Fahrenheit to 65 degrees Fahrenheit after being placed in a refrigerator that maintains a constant temperature of 35 degrees Fahrenheit. Okay, so let me show you what we know here. We know the initial temperature of the soft drink is 75 degrees. So T naught is 75 degrees. Now, the temperature of the environment stays constant at 35 degrees. So TE here is 35 degrees. So that means that TE minus T naught is 40. So in other words, the initial difference in the temperatures are 40. And that's really what that TE minus T naught is. That's the initial difference in the temperatures. So it's 40 degrees. 75 minus 35 is 40. And then we're given, and this is actually the additional information that we're given. We're actually given that the temperature is going to be 65 degrees when time is 5 minutes. So we want to solve for K, so we can solve for the constant. So basically, if I put in this information, I know that T is 65 degrees. I know that TE is 35 degrees. I know that TE minus T naught is 40 degrees. And then I have E to the K times T, but little t is 5 minutes, so we'll just write that as E to the 5K. Now, I can subtract 35 from 65 and get 30 equals 40 e to the 5K. And then if I divide 40 into 30, I get 0.75 equals e to the 5K. And then take the natural log of both sides, so I get natural log of 0.75 is natural log of e to the 5K. Well, we know natural log of e to the 5K is just 5K, so I have natural log of 0.75 is 5K, and now take natural log of 0.75 and divide it by 5, and I'm going to go ahead and use a calculator approximation of 0.05754. Okay, so now if I get basically my initial formula, I didn't give you my initial formula, let me give you my initial formula here. So basically, now that I have that constant, remember I knew that 35 was TE, and I knew that TE minus T naught was 40, but I didn't have K. So now I have this formula that the temperature at time T is 35 plus 40 times e to the negative 0.05754 T. And if I want to know the temperature, say, after 30 minutes, now not an additional 30 minutes, but just after 30 minutes, you put in 30 right here. So put in 30 right here, and then so that means you're evaluating the function at 30. So put in 30 where the little t is, and then basically figure out what is 40 times e to negative 0.05754 times 30. And so that it gave me 35 plus 7.1. So that means it's going to actually have dropped to 42.1 degrees after 30 minutes. Okay, so the temperature at 5 minutes, it dropped to 65 degrees, but at 30 minutes the temperature is 42.1 degrees. Now the next one, the second question says, when will the temperature be 38 degrees? So now I can take this same function and I can put in 38 temperature that I'm looking for, and notice over here in the exponent I have a t. It's kind of hard to see, but there's a t. So I'm going to be solving for that t right there. So basically, if you subtract 35 from both sides, you get 3 equals 40 e to the negative 0.05754 t. And then I wrote it twice for some reason. But anyway, divide both sides by 40, and you get e 3 over 40 equals e to this power. And then 3 over 40 was actually 0.075. So I have 0.075 equals e to this power. And then take the natural log of both sides. So I get natural log of 0.075 equals natural log of this. Well, you know the natural log of e to this power is just going to be the power. And now, so I get natural log of 0.075 equals this constant times t. Now divide by this constant, and you're actually going to get about 45 minutes. So it'll take it about 45 minutes, so about 3 more minutes to drop it down to 38 degrees. Okay, so that's Newton's law of cooling, and it's got some very interesting. Okay, now I hope you don't think this one's too morbid, but it's actually a very practical application of Newton's law of cooling. If you watch crime shows every now and then, you might actually hear it sometimes. Suppose a body is found in a room that has a constant temperature of 72 degrees Fahrenheit. And let's say the temperature of the body is taken and found to be 85 degrees Fahrenheit. 30 minutes later, the temperature is taken again and found to be 81 degrees Fahrenheit. So from those two entries, we can estimate the time of death. So what we can do is we can say our initial temperature of the body was 85 degrees. Okay? And since we know the temperature of the room is 72 degrees, then the initial difference in the temperature of the body and the temperature of the room is 13 degrees, 85 minus 13. So basically, I can put 72 in here for the temperature of the room, and for the difference in the room and the body, the initial difference I can put right here as 13, and I'll get e to the kt. Now, then we can use the fact that when t is 30, the temperature of the body was 81. So how will I use that? Well, I'll just make 81 the temperature, and I'll put 30 in for t, and I'll use that to get my k. So I'll use this information to solve for k. So now I'm going to subtract 72 from 81 and get 9, and then I'll have 9 equal 13 e to the 30k, then divide by 13, and then I get 9/13 equals e to the 30k. I'm just going to leave this as a fraction. And now I'll take the natural log of both sides, so I get natural log of this fraction equals natural log of e to the 30k. Well, we know the natural log of e to the 30k is just 30k, so that would be 30k equals natural log of 9/13. And then to solve for k, divide by 30. So I took the natural log of 9/13 divided by 30, and I got this constant, negative 0.01226. So now, here's my model now. My model is that the temperature of the body is actually 72 degrees plus 13 times e to the negative 0.01226 t. Again, that t just doesn't want to stand out there. But anyway, there's a t there. Now, what we want to do is we want to find when the body temperature was a normal body temperature. And so since we know normal body temperature is 98.6 degrees, let's enter 98.6 degrees in for t, and now let's solve. So for capital T. So now let's solve for time. So if I plug 98.6 degrees in here, I can subtract the 72 and I get 26.6 degrees. And then I have 13 times this expression. And then if I divide 13 into 26.6, I get 2.0462 equals e to this expression. And now I can take logs of both sides. We know how to do that. Take the natural log of both sides. And so here I just get the exponent, 0.01226t equals this log, and then divide this exponent into this log, and I get, or this negative 0.01226 in that log, and I get negative 58.4 minutes. Now, the answer is negative, because it's in the past. So basically, we've determined that about 58 minutes before the first measurement was taken is the estimated time of death. So there you have it. Now, of course, in practice, this is actually entered into a computer program. Let's show you one more. Okay. There's something called a logistic growth model. And so let's take a look at this. We'll talk about white-tailed deer in a state. I'm going to just go through this pretty quickly. The Department of Game and Wildlife sets guidelines for hunting fishing in state, and it's reported estimated 900,000 deer prior to the hunting season 2004. Suppose the deer population that has plenty to eat and is not hunted by humans or other predators will double every 5 years. The exponential growth model is P equals P naught e to the KT, where P naught is 900,000. Since the population doubles every 5 years, then we can put T equal 5 and P equal 1.8 million in, and we can solve for the constant. So the constant, we've done this before, so let's just plug the information in and solve for K, and you'll get 0.1386. So that's the completed model. Now, this assumes, with plentiful food supply and no predation, that the population grows exponentially. Now, that's reasonable in the short term, but consider in the long term, suppose the maximum deer that can be sustained is 2.7 million. That sounds like a lot of deer, doesn't it? Okay, well, then you would have what's called a logistic growth model. And the logistic growth model would look like this. It would look like this. So where you would have 2.7 million on top, that's the maximum sustainable population. And then on bottom, you'd have 1 plus 2 e to the KT. And now if you let t equal 0, you'll see that P would be 900,000, because you'd have 2.7 million divided by 3, which is 900,000. Now, I'm going to plug 1.8 million in here when t is 5, and I'm going to see what this constant's going to be. So, let's see, what am I going to do? Let's see, what am I going to do? All right, well, you can cross multiply here. So if you cross multiply, you get this equals this times this equals 2.7 million, and then you can divide both sides by 1.8 million and get that 1 plus 2 e to the 5k is 2.7 million divided by 1.8 million. So you might put the steps in if you need to. All right, then that's actually 1.5. And then you can subtract 1, divide by 2, and you get e to the 5k is 0.25. Apply your logs, and then divide by 5 to get negative 0.02773. Okay? And so that is now the completed logistical growth model. So now you could estimate that the population after 20 years, just plug 20 in for t, and then plug this in your calculator, and after 20 years, the estimated population would be about 2.679087. Notice how the graph, if you graph this, the graph takes off. It follows like an exponential curve, but it begins to level out. And so right here, you're about at the top end right here, because remember, you can only get about 2.7 million. So it's going to level off after 20 years there. This says estimate the rate the population is changing at 20 years. Now, you need the derivative. So I know I didn't actually show you how to find the derivative, but anytime it asks for the rate the population is changing or the rate something's changing, you're going to need the derivative. So take the derivative. I'll be honest, I cheated here, just used a program. But take the derivative and then plug 20 into the derivative everywhere you see t. And it says, based on this derivative, the population is growing at a rate of 5,754 deer per year at 20 years. So anyway, I hope you found this particular video interesting. I did. And that pretty much completes our discussion on exponential and log functions for this course.